The final projectile example we're going to do is one where the projectile is launched from a different height than where it lands. Okay, so you could do that two different ways. You could have a certain starting height and a lower landing height, or you could have a certain starting height and a higher landing height. Okay, and in that case, you have to be pretty careful about how you solve it, but there are still multiple ways that you can go through it. So I'm just going to show you one way of thinking it through. So from a height of 35 meters, a stone is thrown with a speed of 25 meters per second at an angle of 60 degrees above the horizontal. The stone lands on the ground. We're assuming 35 meters below where it started. Find the time the stone was in the air, how far horizontally it traveled, and the speed and direction of travel at impact. So here we go. We're supposed to first of all draw a picture of what's going on here. So let's say that here is our 35 meters. And the object, whatever it is launched at an angle of 60 degrees from the horizontal. So I'm going to launch it from the very edge over here. So there is the original velocity vector. Okay, so this is 25 meters per second. And it's launched at an angle of 60 degrees. So that's important. So here's our launch angle, 60 degrees. And the trajectory of this object is going to look something like this. There you go. There's our drawing. And so now we're going to use this drawing to determine a way to figure out all of these things that we're supposed to. So part B asks us to find the horizontal and vertical components of the initial velocity of the stone. So that wouldn't be your typical question that you'd get asked about this thing. But again, this question is going to lead you through a whole bunch of steps that you would need to do to figure out kind of your final answer. So let's go to part B. Find the horizontal and vertical components of the initial velocity. That's kind of a standard thing that you're going to do in all projectile problems. So if we know that the total velocity is 25 meters per second, and we're splitting it into a horizontal and vertical velocity with a 60-degree angle going on here, then this is Vx and this is Vy. And so V1y, again, these are initial velocities here, so this is V1y, is 25 times the sine of 60 degrees. Okay, and that gives me 21.651 meters per second. And if I'm going to be using a rounded number like that in the rest of my calculations, I want to keep a few decimal places. So 21.651. So I'm going to reuse that number, and because I've kept that many decimal places, I'll get a pretty good answer in the end. But you could continue using this expression as your V1y if you wanted to. V2, not V2y, V1x is equal to 25 times the cosine of 60 degrees. And just like the other one, you can continue using that expression for your horizontal velocity the rest of the time if you want to, but if you keep a few decimal places, you should get a pretty good answer. But it turns out that there aren't a few decimal places to keep. It's exactly 12.5 meters per second. So those are the initial vertical and initial horizontal velocities. Let's remember that the vertical velocity is going to change over time because of the acceleration of gravity. The horizontal velocity is not going to change over time. And so we didn't actually need to call this V1x. We could just call it Vx because it will be constant. Part C, find the time to the top of the trajectory. So a common way of splitting up a question like this where you don't have the same launch and landing height is by splitting it right here. Okay, and that's a convenient place to split it because we know several things about this. This V2y is equal to 0 there. And then if you look at the second half of the trajectory, you would then call this point v1y. Right? So you would solve this in two pieces. The on the way up piece, where v2y equals 0, and we've solved for v1y now, and the falling down piece, where now your v1y is 0. Okay, so that's a convenient place to split it because it adds another piece of information in there. That's not the only place that you can split it. If you wanted to, you could split it like this. You could make a horizontal line at the launch height, and that would give you a perfect parabola to right there. And then you can use this point as your second half. It's not a half, as your second half of the trajectory. Okay, and there's a different set of assumptions that goes with that, and a different procedure that goes with that. Okay, both are perfectly valid. We are going to go with option number 1, where we split it vertically into two different pieces, into the way up and the way down. Okay, so that's why we're figuring out the time on the way up. Using vertical velocities only, find time to the top of the trajectory. Horizontal velocity does not help us with time, so we are going to figure it out using vertical velocities. So we're looking for the change in time, and we know v1y is equal to 21.651 meters per second. We know v2y is 0 meters per second, and we know the acceleration is 9.8 meters per second squared. Now, we should, just like in the previous question that we did, if you were along for the ride last time, we need to make sure that we have positives and negatives in the right place here, because not all of these vectors are the same direction. So let's call up the positive direction. It's a little bit simpler, but it really doesn't matter. That means that our acceleration is negative 9.8, okay, because it's the only thing in this equation that's actually down. So with those things, we can solve for the time to the top using our v2 equals v1 plus a change in t formula. So when we rearrange this, I'm going to subtract v1 and then divide by a. So I get v2 minus v1 over a. That gets me my change in time. So v2 is 0 meters per second. v1 is 21.651 meters per second. And my acceleration is negative 9.8 meters per second squared. And so the time to the top is 2.2 seconds. Okay, so that is the change in time up. The next part. How much higher is the stone at the top of its trajectory than it was at release? Okay, this is an important piece of information because it tells us how far the object is going to fall in that on the way down part of the trajectory. Okay, so we need to know how high the object is before we can do anything with the second half of that equation, with the second half of the trajectory. Okay, so we want to figure out what is change in dy. Okay, so if we just give ourselves a small version of this thing, we want to figure out what the height is right over there so that we can figure out what we need to on the way down as well as on the way up. Okay, and we need to remember that this height is 35 meters. Okay, so whatever change in dy we figure out right now, we want to add 35 meters to it because that will give us the maximum height. So this is a y thing, so we want to keep in mind all the y stuff that we know. So we know v1y, we know v2y, we know the acceleration in the y direction. We also know the change in time to the top, right? That's not really a y variable, but it's valid in the y dimension and in the x dimension. We can use v2y squared equals v1y squared plus 2a change in dy. You could also use this displacement equals v1 change in t plus half a change in t squared formula to figure out the displacement. That will work just as good. It's just longer, slightly, but feel free. Doesn't really matter which one you choose because you have all of that y information already. So if I'm solving for my y displacement, it's equal to v2y squared minus v1y squared divided by 2a. v2y is 0. v1y is 21.651 squared divided by 2 times negative 9.8. Okay, and our displacement then is 24 meters. That's how much difference there is between the launch height and the total height. Okay, so it's asking in part D how much higher is the stone at the top of its trajectory than where it was launched. Part E is asking us to add up that and the height from the ground. Okay, so this is just 35 meters, which was its starting height, plus 24 meters, which is equal to 59 meters. Okay, and so this is the maximum height. This is the height it's falling from. So that's the maximum height it got to, and now we're going to figure out all the other stuff based on its starting height above the ground. How much time will it take for the stone to travel from the top of its trajectory to the ground? So now we are looking for the time down. Okay, this is all still y calculations. We haven't even touched the x section yet. So we're still going to use v1y, but let's think about this for a second here. We are now on the part of the trajectory that's going like this, right? And so our starting vertical velocity, v1y, is 0 meters per second, right? It hasn't started falling until you start the timer. So our v1y is now 0 meters per second. That's an important thing to keep in mind. We don't know v2y. We can't figure it out yet because we need to know how much time it takes to get to the ground before we can figure out what v2y is, because in this case it's not symmetrical, right? The first half of that parabola is not the same as the second half. But we do know the distance that it falls, and that's 59 meters. Okay. We also know the acceleration, and that is 9.8 meters per second squared. And so now we can think about this again. We can rename our directions if we want to, because now everything is happening downward. So we may as well call downward the positive direction and upward the negative direction. Though, if you would rather keep it the way that you had it the rest of the time, you are welcome to. So what we've usually used to calculate time so far is this v2 equals v1 plus a change in t formula, but we've always known what v2 was, right? Because usually we're talking about where it is at the top of the trajectory, and then we know v2 is 0, or at the bottom of the trajectory, and it was the same as the beginning, so then we could fill in v2 from there. But we don't have v2 in this case. So we're going to have to look a little deeper into the formula sheet to figure out what we're going to use for this one. And it turns out, with the y displacement, you can figure out the time using this equation, plus half a change in t squared. Okay, now this could get real ugly if we're not careful, because if you're solving for time here, this is a quadratic, right? You have to solve a quadratic function in order to solve for time, which means using the quadratic formula. Remember that thing? X equals negative b plus or minus the square root of b squared minus 4ac over 2a. Yep, you can do that. However, in this case, and in most cases, in fact, when you're dealing with problems like this, the v1y over here, it's 0. And so that means that we can eliminate this entire piece of the equation, which means we don't have to use the quadratic formula to solve this thing. Ugh, relief! So, if I'm solving for time, that's going to be, I need to, first of all, multiply by 2, or divide by a half, same thing, and divide by a. So this is going to be 2 change in dy over a, all square rooted. So that gives me 2 times 59 divided by 9.8. Now remember that we've named down positive right now, so both the 9.8 and the 59 are positive. But if we had made negative down, if we had made down negative, then we would have had to make sure that the 59 and the 9.8 were both negative, right? Otherwise you can't even square root that. It's not going to work. So the time is equal to 3.5 seconds. So that's the time it takes to travel from the top to the ground. So now we have the time up and the time down. And that's what part G is asking us for. How much time is it in the air in total? So that was time up plus time down, which is 2.2 seconds, plus 3.5 seconds, which is 5.7 seconds. That is the total time in the air. And that's all the space that you're given for this question, but at the very beginning it asks us to also calculate the total final velocity, and I want to look at that as well. Okay, so I'm just going to carve out some space right over here, and we're going to figure out V2 total. In order to do that, we need to figure out V2y and V2x. We need to figure out the x and y velocity at the end, and then we can put them together in a triangle, right? So if we know that the vertical velocity looks like that at the end, and the horizontal velocity looks like that at the end, we can calculate the total V2 and its angle using those two components. Okay, so we already know V2x though, right? We figured that out at the very beginning. It was 12.5 meters per second. Halfway done. And then V2y, we're going to need to figure that out using an equation. Okay, so we know pretty much everything there is to know about the y stuff going on here, and so we can use the simplest equation that we know to calculate V2y. V2y equals V1y plus a change in t. Okay, V1y is 0 because we're just looking at the falling half of this thing now, and so this becomes hopefully very simple. V2y equals 9.8 times 3.5. Okay, so this is 9.8 meters per second squared times 3.5 seconds. We're using the 3.5 here and not the 5.7 because we're actually only looking at the second part, the falling part of this trajectory. So V2y is equal to 34.3 meters per second. And so now we know that the vertical velocity is 34.3. We know that the horizontal velocity is 12.5. So this becomes an a squared plus b squared equals c squared kind of thing to figure out V2. And then you need to do an inverse tan function in order to figure out the angle. Okay, I'm going to leave you to finish that off, but I will tell you what the answer is. V2 is equal to 36.5 meters per second, and the angle that we're working with, this one here, is 20 degrees, 20.0 degrees. Now, it's hard to describe the directions that are involved in that angle. So usually when we're giving a direction of a vector, then we're going east 20 degrees south or something like that. That's not what this is. But in this case, we're working with up and down as our two directions, right? So you can either say that this is 20 degrees forward of down, which is an awkward way of saying this, but we can actually use a different angle instead. So we can use that one, which is 70 degrees, and then we can say 70 degrees below horizontal. And that gives a bit of a clearer picture. But I am willing to accept whatever set of directions actually makes sense in that circumstance if you want to use the 20 degrees. So we would then say 70 degrees below horizontal. And that's our final answer. Now the last thing that is often asked, what is the range? How far does it travel horizontally? And we've done that before. You're looking for change in dx, so I want to just fill in this last little bit to round the whole thing off. What's everything you could possibly answer? That's what this question does. And that is equal to Vx times the total change in time. And so our Vx was 12.5 meters per second, and our total change in time was 5.7 seconds. And so altogether that gives us 71.25 meters horizontally. And that's the last thing that you could be asked.